I'm talking today on hardcore effects and mean field.
I'd like, of course, to start by thanking the organizers for inviting me. It was a great pleasure, and I felt really honored to be invited here. I feel even more honored being given the last talk in a 3-hour session. So somebody must trust me to keep us all awake. So just do me one favor. If I fall asleep, could somebody wake me up? Okay. So the title is a bit ambiguous. You can't do mean field theories with hardcore effects, of course. What I want to do is supply something that was missing a little bit in this morning's talk on isotopic theory. I want to show how we can actually take into account the fact that these molecules can't just approach each other as they like, independent of their orientation. So I'm going to talk about mean field theories that come from electrostatic attractions, and then how we can get hardcore effects into those. Okay. This is left. Okay. Yeah, I've never worked this one before. Okay. So in principle, for a mean field theory, there are a few steps. The first step is you need to find a two-particle Hamiltonian that describes the interaction energy of two molecules, or whatever your entities are, depending on their relative orientation and relative position. In the next step, you perform an average over space, over the intermolecular vector, to get an interaction Hamiltonian that only depends on the relative orientation. And in the last step, we then use that Hamiltonian to get all those wonderful theories out of the hat, basically. Now, I'm not going to do part 3, as you can see, that's grayed out. I want to do basically only part 2. I need part 1. I need to find a few two-particle Hamiltonians so that I can get started on part 2. But I'm going to find them in the same way that the student who is supposed to find x says, here it is x. You know, these good old jokes. Now, I want to start with something I'm not really that interested in, just because I want to explain a method. I'm trying to be a little bit didactic. I'm going to do a few simple computations so that you see what's going on when I just show you, without doing them, the more complicated computations. So I just want to look at molecules that have a permanent dipole moment. So here's an example, this little guy here. That's the one I'm interested in. And I'm not going to do much with this, just the computations, because they're a lot easier if I look at dipole-dipole interactions than at quadrupolar interactions. So this dipole interaction looks like this. I have, okay, let's give this. Suppose I have two molecules with dipole moments, electric dipoles p and p dash, and then the intermolecular distance, this is 1 over r cubed, the whole story, and here this vector E, that's the vector connecting the two molecules. So what I want to do with this is I want to perform an average over all possible intermolecular vectors E. Oh, sorry. Okay. Now, from this, I get the interaction Hamiltonian by doing the following process. I pick a region in space over which, I need to be a bit more systematic here. So I fix one of the molecules. Opportunity in a lifetime, not to use indices, but to use the blackboard again. Okay, so I pick one molecule, and that has its dipole moment here. And then I say, I look at all the other molecules that have a fixed orientation. There's something like this. Oops, sorry. So this has p dash. And then I take more of those. Another one, p dash. And I move these all about space. And I average all those interactions in the interaction energy that I had first. But of course, I need to pick a domain of integration. And of course, I could integrate over all space, but then I would have one molecule sitting on the other, so that's not so good. So what people usually do is they exclude something, and then the usual thing is to say, okay, I exclude something which is spherical here, and then I get on with business doing my integrals. And that's exactly what I want to do. So I should go back. Do you want to go back with this thing? Oh, yes, indeed. I should go back one step. I think, is there anybody here who's not so familiar with tensors, dyadic products, and all these things, or is everybody quite happy? And okay, good. So I don't need to say all too much about this. But there's a good reason. Sorry? The dot products. The dot products here are just inner products, for whatever the quantities are. Okay. The point is, if you look at the dipolar interaction written like this, it's a scalar product between the dipoles, and in this, here two more scalar products. That looks all very nice. So why would anybody in their sane mind write it in the second form here? Now this is the stands for the identity minus 3 times EE applied to P dash, and then the inner product of this vector that you get out of here with P again. Well, that looks rather artificial, but it has the advantage that everything that I need for averaging is in here, in the center. Namely, I want to do an average over this intermolecular vector E. And the P's, the dipole moments, they are sitting outside. So what I can then do, if I have this, to get my average, well, in principle, this integral sign should have been at the very front. But then all these things here, of course, this number, and also the dipole moments are constants for the averaging process, so they can get outside. And I can just look at this stuff here, no dipole moments, and I just average this guy. Okay, now, yep. This works as follows. So I need to pick some domain here, and what I want to do is I just take an inner ball of radius 2r, where r is basically a radius that has to do with one of the molecules. If I have two molecules and I want to avoid that they overlap, I need 2 times basically the size of the molecule. I need to take that out. So I start at some inner ball, and I go to some outer cutoff radius. Because of the dipole-dipole interaction, I need to finish somewhere here. I can't go to infinity. And then I integrate over S2, the whole story here. Now, and if I do this, this is just wonderful. What you see here is it's 1 over r. It was 1 over r cubed. Of course, from the Jacobian, I get an r squared. So I get only 1 over r. I can integrate this in r. I get this wonderful term with the logarithm here. And the rest is just an average over S2 of this term I minus 3 times EE. And, well, Epifanio had that in his talk. This guy here is actually 0. So there's no interaction energy left at the end of the story, which is pretty good, because if that was my task, I can now go home and we can all go and do something better with our evening. Unfortunately, that's of course not the end of the story, so we need to do something else. So what are we going to do to amend this story? This is not really a physical argument. Do we renounce the spherical symmetry? So do I not use balls, but do I try to be a little bit more specific about my domain of integration that is allowed by the shape of the molecules? That's of course what I want to do. Or do I use a different type of interaction? Well, if there was no physical reason to use a different type of interaction, that would be a very silly thing to do. Of course, this is exactly what Meyer and Saupe did. They went to induced dipole-dipole interaction, which is basically a quadrupolar interaction, and did this. So they must have thought that this first way here is way too complicated. Let's just do this. No, it's of course not really what they did. What I want to do in a while is I do both. I go to the Meyer-Saupe interaction. That's what I really wanted to talk about, the Meyer-Saupe type interaction, as in this morning's talk. And I want to introduce the sterical, the steric effects. Okay, now a bit of light entertainment. That was inspired by Tim's wonderful talk yesterday. Okay, so this is actually pertinent to what I want to say, because Meyer and Saupe, what they did, you saw that this morning, they just did exactly the same type of integration with the same type of domain. They just used a big ball with a little ball cut out in the center, and their ball actually extends to infinity, and they just said, well, who the heck cares? Well, actually, they didn't say who the heck cares. There are 3 papers that were written back then. I think Tim has translated the first of those. That's a very short paper that just gives the gist. The other paper is a bit longer, comes in 2 parts. In the second part, you find this wonderful thing here. This is not a single sentence, I have to point out. It might have more than 100 words, but it was not written in 1888, but in 1960. Okay, so let me just point out a few things. I'm not turning this into a German lesson. The wonderful thing here is einfach. That means simple. This is a simple theory. Oh, aren't we all happy? Okay, now what they say here is this says that the steric close-range ordering can be incorporated into the Meyer-Saupe theory. So when they did that, they already thought about it at that time. Okay, albeit in a very simplified fashion. And how simplified, I'll show you in a minute. Okay, this is this next one here. So instead of using a molecule for your statistical treatment of the problem, you use a group of molecules. What group of molecules, and why would you want to do this? Well, and that's where it gets slightly dodgy. The smallest group of parallel molecules. You can almost read that in English. Huh? The smallest group parallel molecules, I can see this here. So you take the smallest group of parallel molecules that are approximately spherical. Well, what on earth is that going to be? Well, doesn't really work. But basically what they say, you look at the aspect ratio, and if you take a few of those molecules and you, sorry, it's my way of keeping you awake. So if you take the right number of these, then you get a sphere. Well, if I look at this, I get a cube. But well, for this type of interaction, a cube is as good as a sphere. So we can probably stick with this for now. So now the last bit, the last sentence has nothing to do with this really. It says the justification of this move of looking at groups of molecules that are spherical, and then I can of course do all the spherical averaging. The justification of this, well, the experimentalists have to do this. They have to check whether what we do here actually works. No? Okay, so that's very sensible. If you're a theoretician and you're not so sure, I just say future generations will find out whether this was any good. Of course, in this case, we all know that it was pretty good. Okay, now, before I can actually go into this computation of with the steric hindrance, I want to talk a little bit about the Hamiltonian that I hope to get out of it, because I want to show you what the effects are of incorporating the steric hindrance on the interaction Hamiltonian. And if I don't know anything about the Hamiltonian, that will be very difficult to explain. So that's a small deviation from the main course here. So I go back to the molecular tensors. I'm launching straight into biaxials. So I have this guy here with a main, oops, that was wrong again. Okay, with a main axis and two secondary axes. And if you want to think uniaxial molecules, you have to ignore these two guys here. So if I have this general one, I get two molecular tensors, both symmetric and traceless, this little q tensor, this little b tensor. And if you want a cylindrical symmetry, this b is just not there. Okay, so whenever I talk about the uniaxial molecules, all the terms of b will just simply be 0. Okay. Now the most general quadrupolar interaction that I can build with these terms has the following form. And this is, okay, Q and, well, I need a bit more information here. Okay, so Q and B are the molecular tensors for one molecule, and Q dash and B dash are the molecular tensors for another molecule. And these guys are just rotated versions of the first one. And this rotation is the rotation that takes one molecule into the other. Okay, and I need O3 here because I've got biaxial molecules, so okay. Now, in here I've got 3 parameters. Here's an interaction strength. The first parameter, this psi guy here, this is either plus or minus 1, depending on whether I want attraction or repulsion here. And any other normalization is in this U0. And then I have 2 more parameters, this gamma and this gamma and lambda here. That this one is the secondary tensor, if you want, that we only have for biaxials, and this is the coupling between the biaxial tensor and the uniaxial tensor. Okay. Now, let's leave this out. If I have uniaxial molecules, as I just said, then all that happens is I have Q and the B's are all 0, and H from the preceding transparency is just reduced to this guy here, which is just the usual Meyer-Sauper interaction that you get here. Okay, let's leave that out. I'm trying to be quick. Okay, now as it turns out, and this involves a lot of algebra, and this is the start of the computations that I'm not going to do, it is possible to rewrite this Hamiltonian in terms of just 2 tensors. Well, it was in 2 in the first place, but with just 2 terms, with 2 tensors Q plus and Q minus that are orthogonal to one another. So this is an inner product between 2 tensors here. Okay, and then there's all kinds of relationships between these 2 guys here, A plus and A minus. They depend on the lambda and the gamma that I had in the original one. Okay, now I can, sorry, maybe I should go back once more. Now, in this form here has the advantage that I have a quadratic here and a quadratic here, basically. And I can look at this A plus and A minus and can decide on the nature of my interaction. And this looks as follows. If both A plus and A minus are positive, then I call my interaction fully attractive. That's the case in terms of the original parameters in the first interaction if lambda is greater than gamma squared. And if one is positive and one is negative, that's the case when lambda is less than gamma squared, then I call the interaction partly repulsive. And finally, it could be that lambda equals gamma squared, then the whole interaction can be written as the interaction of a single tensor, namely this guy here, Q plus gamma times B with itself. Now, I should maybe have mentioned a few names here. This type of interaction is actually what started the whole affair of biaxials in 1970. That's what Fraser posited, albeit not quite in this form. He didn't know about our wonderful Q and B tensors then. And if you go back to this one here, this is the modern way of writing Straley's interaction in 1974. So this is what we have here. Okay. Now, I think I'll stick to my promise not doing any of this mean field stuff. I'll just fast forward. Okay, steric hindrance. Now I can come to the to the core of my talk. Yeah. Trying to make it soft. Okay, so my first task was to find an interaction energy that depends on the relative orientations and the relative relative positions. Here it is. So that was the story. This is a dispersion interaction, and that's already written in a funny way. We've seen exactly this morning, though not quite written in this form. So there's some constants in here, some interaction energies. 1 over r to the 6 is worth pointing out. And there are some tensors, capital U, second-rank tensors that depend on the intermolecular vector ER. And A1 and A2, these are molecular polarizabilities. Those are also tensors of the rank of second rank. And if I tell you what these symbols mean, I think Epifanio had that yesterday. Let me see. That's this guy here. This is a funny product here between two second-order tensors that gives you between two second-rank tensors that gives you a tensor of rank 4, and this is defined by its action on a tensor of rank 2. So this guy here takes any tensor C and just sandwiches it in between. So if I decipher this term that I have in the interaction energy, it basically looks like this. It's the first polarization tensor, then U times second polarization tensor, and the same U again. And the reason for writing it in this funny form is the same reason that I wrote the dipole-dipole interaction in this funny form, because now this has everything all over the place, the A1 and the A2. But if you look at this, I have actually a fourth order tensor acting on this guy, and afterwards I take an inner product. I can take this out of an integral. Oh, sorry, not this one. I can take the other guys out of an integral. So that's the reason for writing it in this funny form. Okay. Yep. This is one more bit of information that I need for telling you a few things. This U tensor has actually the form of ER minus 1/3 the identity. So a symmetric traceless tensor, depending on the vector ER, unit vector, in the direction from one center of a molecule to the other. Okay, now let me see. This is the main picture. To determine my domain of integration for the averaging, I need to look at my molecules. And I imagine that for each molecule, I have a sort of region that is impenetrable to the other molecule. Now, that is for the physicists to debate in detail where you get these regions from. I just imagine that there is some such region. And then here are the charge centers. And then what I do is I fix one of those molecules and then move this other molecule around and let it explore all of space as far as it can. And that gives me a region that I will then use as a region of integration for the averaging process. So that looks basically like this. So the same two guys as before. This one, as I said, is fixed in space, and this one is moving. Here is the point of contact of the two guys, the two normals, and then this dashed line here, this is a sketch of the path that the second molecule would trace if it were to move along this, but staying in contact. So once I'm all the way around this guy, of course I have to do that in 3D, I have then identified this excluded region R and its boundary, and then I can use that for the averaging.
The orientation of the second one is fixed.
They're both fixed.
So that dotted line, why does that dotted line look so much like the arc?
I said it was a sketch. It's actually not a very good sketch.
You don't intend it. Right?
It's not intended to be a circle, no. It is something which well, if I go back to this guy here, what I really want, it's probably better to use a simpler molecule and not one that looks like a potato. You know the problem with people who from time to time have to teach continuum mechanics, all they can ever draw is a potato. So obviously, if I have some sort of ellipsoid, and I take another one that then might sit here like this, at this angle. If I move that to here, then this point goes here, so I get something which, well, the way I draw it, it will look like a potato again, of course, but so it's not meant to be circular. This just came out of thoughtlessness, I suppose. Okay. Okay. Now, this is what I would like to do. I want to get the two-particle Hamiltonian that doesn't depend on the intermolecular vector by performing this average. So this is Euclidean space, and this is R. So it's everything apart from the Euclidean, from the excluded region. Okay. No. The problem is, of course, these regions can look rather tricky and difficult. You might not be even able to find them properly or easily, depending on the shape of your molecules. So, okay, let me see. I think I temporarily lost my bearings with my own talk. But as long as I don't lose the orientation, I'm okay with liquid crystals, I suppose. Let me see. I've done here, yes, okay. I need to go back one step. Okay. Okay. I want to do now the same trick that I did when I worked with the dipole-dipole interaction. I want to do the radial integration first and get rid of this, and then be left over with an average over S2. But in order to do this, I need to assume something about the nature of the excluded region. I can't do that for an arbitrary molecule or an arbitrary shape. Now, what I want is somehow. Okay, I want the region to be star-shaped. Now, again, for a potato, no, it just has to be a star-shaped potato. So I want a region that I can obtain from by a very simple mapping from S2, and that I start from. I start from a circle, deliberately small so that you cannot see it at the back, because I don't want to draw attention to it. And then I blow this up in such a way that I still have contact to the point in the center. So if I have this point here, let me see whether I can manage. Oops. Okay, let's make this a little bit nicer. So this is a star-shaped region. It's a bit like a starfish if you want, as long as the starfish keeps its legs straight. And then if I go to this point in the center, I can then reach an arbitrary point here, anywhere, and I can get to all the points. I can still, that's enough. I can still get to all the points in the star-shaped region, in particular to all the points on the boundary, which is what I'm going to need. Okay. So the crucial bit here is the shape function, U star. So I have the distance between 2 points in this region is r times a unit vector, and this r is less than this shape function, and this depends on where I am. Exactly as you can see here. It's pretty short here, but I can go a long way here. So that's this U star function. It gives me the length of those little lines. Okay. Now, if I do this, I can perform the radial part of the integration. I do the same as before. I write the whole thing in spherical polars, and then I had an 1 over r to the 6 in my interaction. I get an r squared from the Jacobian. I do an integration, and the integration gives me 1 over r cubed, and I put in my two limits of integration. The lower limit of integration is exactly where this excluded region stops, and the upper limit of integration is infinity. Well, 1 over infinity cubed, I'm very happy with that. So I get something which looks like this, and my interaction is almost done. So the Hamiltonian is now this funny guy here. This is what we call the steric tensor. This is tensor of order 4. That's the average of this construct here over, including this one over u star cubed over S2. So now, if only I could find somebody who can compute this average for me, then I would have my Hamiltonian. In general, I would have to rely on my friends from the computer science department to do this. Could be done in principle. I think Epifanio had a project running with a computer scientist, but as far as I know, that's been running for 4 years now. I haven't seen a publication. I'm not sure. Maybe shouldn't. I see. Maybe I shouldn't have touched upon this issue. It's delicate. So when we came up with this first, we thought, well, obviously this is not something that's easy now. It might look simple. The form is simple, but what can we do? Well, we actually went a little bit further. We went to shapes that are almost a sphere and slightly deviate from the sphere, where we can actually do computations and then see what this actually does to our interaction Hamiltonian. So this is the next part. Now I'm looking at almost spherical shapes, and okay. So we represent the shape of the excluded region in the following form. I choose. Oh, where are we? Okay. Okay, I have a unit vector u of ER. That's the one that goes from P up to here. And this is some given radius that I start with, the radius of the original molecule that's undistorted. And then I add a little vector, add a little epsilon that depends on what direction I go in. And here's the function v that depends again on where I am. Okay, and if I do this, it says the shape in this family is convex if epsilon is sufficiently small. I'm not sure how small it needs to be, but of course, if you start from a sphere, and if this function v here is reasonably well behaved, then it will be convex at least for a while. So, and we're only going to do the asymptotics. Okay, now that is still a little bit too general. Now the next thing I want to do is I develop this function v into a multiple expansion. And I get several different moments. Here's the first one, shape dipole time, that's a vector, scalar product with ER. Then there's a shape quadrupole, scalar product with, okay, now I need to explain this guy. This means, this little bar on top here, this means the symmetric traceless part of a given tensor. Now all these tensors that you see here in this multiple expansion are already symmetric, but they're not traceless. So we need to take the traces out, so that this term and this term and this term and all these terms are actually independent. Because if this has a trace, there's something else in there that I don't want. So it's basically a kind of orthogonal expansion. And there is no zeroth moment. I'm starting with the first moment because I have a property here. I want that the average of this function of v that I add to my radius is 0. Because if the average of this thing is not 0, all I do is a translation of the ball, which is, well, I'm not interested, frankly. Okay, now there's another observation. Oops. This wonderful fourth rank tensor that I want to average over, that is actually even in the intermolecular unit vector. So once I do the averaging, all the terms that have an odd number of ERs in there will disappear because I'm averaging over all of S2. So the first non-vanishing term is this guy here. And we weren't crazy enough to look at the fourth order shape tensor here, so we just stuck with this one. So we just say, we take the first one that doesn't vanish and it gives us something, and see what type of results we can get from this. So this guy E here, this can be computed because it's basically a coefficient in this expansion, can be computed the other way around by computing the average of the unknown function v, or maybe a given function v if you want, with this basis tensor here. And then there are all these funny factors, 15 over 2 in front of this one that you get with these Cartesian tensor expansions. Okay, now see what I have here. Okay, now here is the result of the averaging with this guy. So if I use this quadrupolar shape tensor, I can compute the average explicitly the integral, and I find that then my Hamiltonian that still had the A1, the A and the A dash in, that the Hamiltonian takes this particular form. So there's a number in front, there's okay, and then you've got all kinds of inner products between these polarizability tensors. And this A naught, that's the traceless part of the original polarizability tensor A that I had. So this is the general format for a slightly disturbed sphere. And now what I need to do to get theories out of this, Hamiltonians out of this, is I need to plug in explicit expressions for A, for the polarizability tensor. Okay, now we had that before, for good reason. Now, the polarizability tensor can be written in terms of the identity and this Q and this B tensor, and that's what I want to do. That's why I have this again. So now we just look at a special case, because in principle, this E shape tensor can be anywhere, can point in any direction if you want. But given that we already have the polarizability tensor, to keep things simple, we assumed that this shape tensor shares the same eigenframe with the polarizability tensors. In that case, it can be written as some number times Q plus some other number times B. These are exactly these two tensors. And because this guy here is traceless, we don't need the identity. So that's the most general form of a symmetric traceless tensor that has the same eigenframe as these guys here. Okay. Now, for general biaxial molecules, and that's something that, again, that we had this morning, these polarizability tensors look like this. So A is something times the identity, something else times Q, something else times B. These something else things, of course, have a very definitive meaning. If you think of permittivities, this alpha here, that's the average of all the three. Alpha 1, 1, alpha 2, 2, alpha 3, 3. Those are the eigenvalues of the polarizability tensor. And here is the major anisotropy. So this here would be a minor anisotropy. This guy is only present if we actually have a biaxial molecule. This guy would be there also in a uniaxial molecule. So I need the first two for Meyer-Sorpe and all of them for going a little bit further. Okay. Now, after turning the handle for a considerable amount of time, we find that the Hamiltonian takes the form of all the stuff here, which looks exactly like the Hamiltonian that we had in Straley's interaction that I showed earlier, but we have explicit expressions for these coefficients A, B, and C that are related to these permittivities. Right? This is a bit longish here, so I'll look at a few special cases to interpret what's going on here. Okay, now maybe the easiest one is Meyer-Sorpe. So I should go back. So if there's no B, no, sorry. I'm missing something. No. I don't, in the Meyer-Sorpe case, delta alpha perp is 0. So this guy disappears. If you look at the last term here, this is all multiplied by delta alpha perp. So this disappears completely. So what happens is that I get these three coefficients. Now, this is not Meyer-Sorpe. And Meyer-Sorpe, I want only the QQ. Well, if I go back one, this is the only term I know from Meyer-Sorpe. So I get something which is here, even though I started from the same type of interaction. These guys have cheated us. By doing their dodgy average, we missed out on something. Well, it turns out it's not actually so crucial, because we get an effectively biaxial interaction, but as has been shown relatively recently, even if you look at this type of interaction, then you always get a uniaxial phase. So they have cheated only slightly. They haven't even cheated us of a phase. So in that sense, not even experiment justifies what they've done with their averaging, but even the theory justifies what they've done. So I think that's rather neat. And of course, the last bit, if the shape is spherical, then these parameters rho and beta are 0, and then all that remains, is indeed the old Meyer-Sorpe interaction. Okay, in the biaxial case, I'll want to do this the other way around. I look first at the case where the shape is spherical and see what I get. That's my standard interaction. What I have then is that I have these values here, and then I can, well, I've done it slightly differently when I introduced that about half an hour ago. But you might remember that I classified these interactions according to whether they were fully attractive, partly repulsive, or simply attractive. So in terms of these A, B's, and C's, I need to look at B squared minus AC. There's a factor 4 missing here because we missed out on a factor 2 in the definition of this B guy. And other than that, it's basically just a discriminant. So this is 0 for my interaction automatically. So the interaction is simply attractive. So this is basically, in a way, what Fraser had predicted. Now, if I look at the complete picture, I can still compute explicitly, relatively easily, this B squared minus AC. It's a rather lengthy expression, but it is a perfect square. So this to the power 2 is for this bracket here. So this guy is automatically always greater or equal than 0, which means either I still have the Fraser type of interaction, or I have a more general Straley type of interaction, but only of the partly repulsive form. I never get out of this a fully attractive interaction. Well, I wouldn't have expected this, because I start with an attractive interaction, and then I compute the effects of the steric hindrance. So this makes perfect sense. But of course, in a way, it is bad news for those guys who still think that Fraser interaction is enough to describe everything, because even if you start with this, the moment you incorporate the steric hindrance, you find that this is no longer necessarily 0. So it is normally greater than 0, and you have to look at the full Straley type of interaction. Okay. Well, I kept this for last because I didn't know whether I would get that far, but obviously I made good progress. This is where I left off with my little toy example of the dipole-dipole interaction that we actually looked at for a different purpose that I don't want to talk about. But after keeping you on tenterhooks as to what happens if you do it properly there, I can do this very quickly. So we have the same type of interaction here. I look at a Hamiltonian. I look at the excluded region. I again look at a star-shaped region. I have the same shape function U star here, and I can compute the average of this tensor here. This is now a second-order tensor. So I would say order tensor, second-rank tensor, and it takes this form here with this logarithm. And again, if I use a spherical shape, if the shape is spherical, and you can see that relatively easily because the only dependence on the shape sits in this guy here. And this one here, of course, that's average over it. So if it is spherical, then there's no real dependence on where I am on my unit sphere. Then this can go in front. And then I have this average again here, and the whole thing is 0. So that's what I had before. Now, if I renounce from saying this must all be spherical, if I allow a shape that is a bit more interesting, and again, spheroidal shape with a shape tensor again of the second order, then I get this steric tensor, and I get this type of interaction. So I actually get a Hamiltonian out of this that is non-vanishing. It has a slight disadvantage that it looks all very nice. I just wrote some U0 in front of it, but because this is proportional to the distortion that I do to my shape, it is actually order epsilon. And so it might be so small as to be meaningless. So I think, well, maybe while the credits are running, or rather stationary here, what I would like to see, this is supposed to be the final sentence of the day. I better make it a good one. Okay. So I think, I hope I convinced you that this is a worthwhile enterprise because we see new effects, things that we don't see without taking into account the steric hindrance. The problem that we have so far is that we don't have a good way of computing these tensors. So that might give rise to some discussions, and maybe somebody who has a good idea on how we can push this forward. That might be something for the next 6 months. And with that, I want to finish and thank you for your attention.
Very much.
This thing, of course, has been derived before in spherical, in the reducible tensor, which is equivalent. And personally, I think it is simpler and perhaps even more elegant if you deal with the rotations. That is just a point that we can discuss. But I think all of us that come from the molecule side would do this type of introduction of steric term in a different way. You would have a term which is actually coming from steric repulsion added to the attractive Hamiltonian. This is what you do all the time. For example, even with spheres, if you take Lennard-Jones, this is actually the sum, if you like, of always attractive, because dispersion forces are always with the negative sign, plus a repulsion force. Then in this type of problem, I think what we have is simply we decide on a shape, which could be an ellipsoid or whatever, could be a disk, could be whatever. And then rather than calculating this integral, we have what we would call a kind of contact function, or in any case, we take care of the fact that when the molecule get too close, they will repel each other. So I think the result would be, it is the same, it has to be the same, but it is a lot more easy to compute. And personally, I think, I think there are a couple of examples. For example, for spherocylinders, the excluded volume surface was calculated exactly, I think, by Gelbart, and there are some other cases. But if you take more complex cases, it will be very difficult. While in the other way, it is kind of doable. I could show some example. We have taken cups, bowls, or all sorts of other things, which would be very difficult to calculate. Let me make two other little points, since I'm spending a lot of time on this type of problem. One is that there is an hidden assumption here, of course, that we all use, that the dipole you use is a point dipole. And the point dipole approximation is actually not a very, very good one for real liquid crystal, because molecules tend to be aromatic, flat. And so the radius of convergence of that multipolar series, is actually beyond what is actually reached in practice. In other words, molecules get here, and the two charges here don't, they are not so far, so that they allow. This is not for your talk, which is perfectly, but in general.
You can reinterpret the shape as whatever you like.
No,
it doesn't necessarily have to start.
The multipolar expansion with a point dipole or a point multipole does not converge.
If it does not converge at all, then of course.
It does not, because you are going inside the radius of convergence, because the multipolar expansion is for distance bigger than the distance from, well, as you know. Can I make one last comment? You showed, of course, that the isotropic average of the dipolar interaction is 0, which is clear because it's a traceless tensor. This does not mean, of course, that dipoles are irrelevant, even for a spherical isotropic distribution. If you consider thermodynamic perturbation theory with an isotropic reference, then the first term in perturbation would be what has been evaluated, which is 0. But actually, if you go to the next term, just because the first one is 0, it will carry a negative sign and be a stabilizing interaction.
Yeah, I didn't want to make the point that this is a useless type of interaction. No, you're perfectly right. No, I just used this as a relatively easy computation to show what I was doing with the fourth order tensor.
I wonder if it might be worthwhile to take the other approach. Here you're doing a perturbation on kind of Meyer-Salpa type thing by putting in a shape thing, but one could put in attractive interaction into the Onsager model.
Okay.
And approach it from that perspective and see how close things are.
Right.
Actually, I wanted to say exactly the same, because that solves your problem.
Yes, exactly. Yes.
And it does take care of hardcore interactions automatically if you do like averaging of Meyer's function rather than interactions, right? And it produces
actually, if I can, this is really kind of density functional theory when you do the averaging by using as a reference the steric pair distribution. And the simplest approximation to the steric pair distribution would be the low density limit, would be e to the minus beta u.
Yeah.
So that could be the function one could use to average.
Yeah, that's what is called short-range steric correlation.
Well, okay. It's a special case of density function.
Well,
questions?
I think it's a good project.
Worn out? Everybody worn out?
No.
Okay, so thanks so much again.